Hey, it's Kevin again. Let's talk about layer 2 of the USI model, the data link layer. At the data link layer, we've got a couple of sub-layers. Check out this graphic. Notice that we have a MAC sublayer, that stands for Media Access Control, and we have an LLC sublayer, that's the Logical Link Control. What's going on at the MAC address sublayer? Well, one of the big things, the first thing I think of is physical addressing. A MAC address, a Media Access Control address, that's a 48-bit address that's burned into a network interface card. The MAC sublayer also deals with logical topologies. Down at the physical layer, we're dealing with physical topologies. How are things physically interconnected? We might have a token ring network, for example, with stations physically connected in a hub and spoke topology, but logically, those tokens going around the token ring, they're going through a logical ring. So the logical topology, that exists at layer 2. The MAC sublayer also deals with how we transmit our media. I mentioned token ring, that's more of a legacy LAN technology these days, but the way token ring worked is there was a token that was passed from station to station in a circular fashion around this logical ring, and when a device was in possession of the token, if there was an opening in the token where it could insert its data, it would do that. It would insert its data and pass it on around the ring until it got to its destination. We're more familiar with Ethernet though. Ethernet, in its original form, used CSMA-CD, carrier sense multiple access with collision detection. That was a way for Ethernet to listen to the wire, to make sure no one was transmitting right then, and if the coast was clear, then our Ethernet device could transmit on this Ethernet segment. But if two devices happen to be listening at the very same time, it's possible that they could transmit at the same time, resulting in a collision. When two devices on an Ethernet segment transmit at the same time, a collision results. That gives us data corruption. And CSMA-CD, the CD says that we're going to detect such a collision, and that's going to allow these stations to back off for a random amount of time, and then they will attempt to retransmit their data. What about the LLC sublayer? One of the things LLC is concerned with is connection services. Connection services deals with flow control. If the sender is sending too rapidly, a flow control mechanism can ask it to slow down. Error control, that's part of connection services, and error control is a way to let the sender know that the expected data was not received. Something else we have at the LLC sublayer is the synchronization of transmissions. Senders and receivers, they need to coordinate with one another when a data frame is transmitted and when it should be received. One way of doing that coordination is an isochronous approach. With isochronous, the devices, they can look to a common external device for clocking, and this external device is going to create fixed time slots. Then the devices can determine if a time slot has any free space, and if it does, it can insert the data in that free space. This gives us very little overhead. Another approach is asynchronous synchronization. With asynchronous synchronization, the devices, they can reference their own internal clock rather than having a common clock, and they're going to use a start bit and a stop bit to indicate the beginning and the ending of a frame. And to detect any errors, it can use parity bits. For example, if we have a frame of 8 bits, we could stick on an additional parity bit, and if we're using even parity, if we add up all the ones in the 8 bits in the frame and we add on the parity bit if it's a 1, or we don't add it on if it's a 0, if the total number of ones is an even number, that's an indication that the data has not been corrupted. You could also do odd parity, where you're looking for an odd number of ones. Of course, the bad thing about parity bits is if you've got a couple of errors, well, unfortunately, 2 wrongs do not make a right with parity bits. You could get a false sense of assurance that the frame has not been corrupted when really it has. And one other one for you, synchronous synchronization. With synchronous synchronization, the sender and the receiver can share clocking over a separate communications channel, and for error detection, instead of using parity bits, they're going to use an algorithm called a CRC, a cyclical redundancy check. Let's think about what sort of network hardware would reside at layer 2. Here I've got an Ethernet switch. This is a Cisco Catalyst 3750 Ethernet switch, and you see I've got a series of ports along the front of the switch, and we can have end stations plug in to these ports. And what's the switch going to do? The switch is going to learn the MAC addresses of the devices plugged into those ports. Kind of works like this. Let me give you a diagram. Let's check this out on a flip chart. Let's say that we have a catalyst switch that looks a lot like a pizza box when you draw it out. And we've got a couple of ports. Port 1, port 2. And just as a time saver, I'm not going to write a full 48-bit MAC address for these PCs. Let's draw a couple of PCs. And I'm just going to give an abbreviated address. I'll say it's AAAA. An actual MAC address would be a 12 hexadecimal digit address. I'm just going to write 4, just for brevity's sake. We'll say we have AAAA and BB. And the MAC address table is going to be constructed inside of the switch like this. We're going to say, for this port, we've got a corresponding MAC address. For port 1, we've got MAC address AA, and for port 2, we've got MAC address BB. And to illustrate this a bit further, let's go out to some live gear right now. Let's go out to a actual Cisco Catalyst 3750, and let's take a look at what MAC addresses reside on which ports. Let's go into the switch and let's say show MAC-address. And the Catalyst switch has some built-in static addresses. But I want you to notice as we scroll down just a bit further, notice the dynamic addresses. Notice that we've got MAC addresses. Let me highlight one for you. We've got these MAC addresses that have been learned off of different ports. So the MAC address you're seeing right now has been learned off of port Fast Ethernet 1/0/2. And something else I want you to notice, take a look at the Fast Ethernet 1/0/1 port. There are several MAC addresses learned off of that one port. Is that possible? Yeah, it sure is. You see, what's happening here, it's not just we can have one device off of a port. There's a switch connected off of a switch port in this case. And that's perfectly fine. We can learn devices that live off of a switch connected into a switch port. Where does this stop? Well, it stops at a router. That's a layer 3 concept we'll talk about next time. But right now, we're able to go into a switch and we're able to see what MAC addresses reside off of which ports. What's the purpose of this? What good does this do us? Well, think about when a frame comes into a switch. The switch, instead of just flooding that frame out of all the ports other than the port the frame came in on, the switch can intelligently forward that frame because it knows where it's destined. For example, remember on the flip chart, I showed you we had a PC with a MAC address of AAAA and it lived off of port 1. Well, if the switch receives a frame coming in another port and it's destined for that MAC address, the switch knows that it only needs to go out of port 1 because the switch has already learned that that PC, AAAA, it lives off of port 1. This is going to allow at layer 2 a switch to intelligently forward traffic. Now a router at layer 3 can do some intelligent forwarding of its own. That's the topic of our next video. We'll see you then.